Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion on the spatial part of spatial data. Specifically talking about how we can model continuous spatial data. So in the previous video, we talked about vector data having discrete coordinates and being able to measure things with discrete boundaries through points, lines, and polygons. But how can we tackle this idea of something that is continuously changing over an area? Right, and we used the examples of elevation, climate and weather data, etc. Well, what we're going to do is we're going to implement something called raster data, or the raster data model. Where we are basically going to take an area, break it up into regularly sized grid cells, and then assign a value to that grid cell that represents whatever we're trying to measure for the area that the grid cell is over. Okay, so let's go ahead and give ourselves a little bit of space here and make this a little bit more formal. So we're talking about this idea of raster data. So whenever I talk about raster data, I find it helpful to sort of hold in the back of your mind this idea of a computer monitor or a picture that you've taken with your cell phone, because the structure of raster data is very similar to those two concepts. It's just that what we're actually representing is a little bit different. And so with raster data, sort of broadly speaking, what we do is we break an area up into see if I can make that a little bit cleaner, into evenly sized grid cells, and assign values to those grid cells that represent the area of the grid cell. Okay, so what does this look like when I say we break an area up into evenly spaced grid cells? Well, what that means is, let's say that we're trying to examine, we have some area, which I'm just going to draw kind of randomly. Right, so this is going to be our area. And maybe we're interested in looking at rainfall amounts, right? How much rainfall does any given piece of this area get? Well, if you've ever been outside, you know that rainfall isn't consistent, right? It's a continuous data set. It changes continuously across this entire area. So what we can do here, and I'm going to do this in a different color, is we can break this area up into evenly sized grid cells. Now, my drawing skills aren't that great, but these squares are supposed to all be the same size. right? So we have our area, and we've now broken that area up into a series of evenly sized grid cells, right? So each one of these boxes here, right, this box, this is a grid cell. Sometimes you'll hear it referred to as a cell, simply as a cell, or sometimes you'll hear it referred to as a pixel, right? Grid cell, cell, and pixel are all sort of synonyms referring to a single square in this larger thing, right? This larger thing here, this is called a raster, right? So a raster breaks up an area into many evenly sized grid cells. These grid cells are arranged in rows. So you can think of this like an Excel spreadsheet, right? You have rows which go horizontally, right? So this would be row 1. So let's do that in a different color. Right, this would be row 1. Right, this would be row 3, row 5, etc. Right, so rows are horizontal runs of pixels. It also uses columns, right? So column 1, so this would be column 1. Right, this would be column 3. This would be column 5, right? So all a raster is it's a group of evenly sized grid cells arranged in rows and columns to cover the area, right? And again, the reason why I said I like to kind of hold in the back of my mind this idea of a computer monitor or a digital picture that you took with your cell phone is because this is exactly what computer monitors are, right? Your computer monitor is nothing more than a rectangular array of evenly sized, in this case they use the term pixel, right, that is projecting light out of it to hit your eye so that you can see the stuff that I'm drawing on the screen, right? It's that same concept of an arrangement of evenly sized pixels or grid cells. And so what happens here then is this grid cell, let me pull out one grid cell. Right, so I'm going to pull out one grid cell. So we'll pull out, right, this grid cell. So this is a single grid cell. And again, I could be using the word cell or the word pixel. And there are some things about this grid cell that we need to keep track of. The first is the value. I'm running out of colors here. The first is the value, which I'm going to denote as an X on the inside of the pixel. Right? This is the cell value. And the cell value is going to be, this is the information, right? The cell value is the information. Right. And so if we were to go back to the example that I kind of began when I drew out this sort of blobby area here, right? If we were to talk about measuring the precipitation, right, the amount of rainfall that was occurring across this area, right, this cell value would be the precipitation that is represented for the area that this grid cell covers, right? And so if I were to say that, if we were to just say that this grid cell right here for precipitation had a value of, say, 14 inches, right, I would be saying that the area underneath here was represented by 14 inches of rain, received 14 inches of rain. Okay, so again, cell value is just the information, right? It's a number. And so The second piece that we need to be aware of is the length of one of these sides. Right, the length of one side is referred to as the cell size, or more often in readings, you'll see it referred to as spatial resolution. Spatial resolution. Right, so again, spatial resolution is a measure of the length of one side of a single pixel. In fact, I'm going to rewrite this again because this is going to be very important when we talk about different scales of information. And spatial resolution is going to be immensely important when we talk about remote sensing, which is one of the ways that we generate raster data. So just to really clarify this idea of spatial resolution. Spatial resolution, I'm going to put underneath it cell size, because again, right, you'll see both these terms, right, just like grid cell, cell and pixel are synonyms. Cell size and spatial resolution are synonyms, right? Spatial resolution is the length along one side of a single grid cell. Okay? So with this information, right, the idea that a raster is an arrangement of grid cells in rows and columns, and that each grid cell contains a value that represents the area that is under that cell, and we can determine the size of a cell by specifying its cell size or its spatial resolution, we should have a pretty solid understanding of how rasters work. And as we come across more and more examples, this will hopefully become more and more clear. And there's going to be some other terminology when we get to remote sensing that we're going to throw in on top of this. But just understanding this concept is 80% of the way there. What I want to wrap up this lecture talking about is how we locate rasters, right? How do we bring the location aspect in, right? Because with vector data, it was fairly straightforward because the vector data itself was just a string of coordinates, right? But for this, we haven't actually specified how do we know where this grid cell even is, or this arrangement of grid cells, where this even is. And then two, I think it's important to talk about the trade-offs between spatial resolution, cell value, and data volume. So let's tackle that first question first. How do we actually set up, or how do we know where these grid cells are? The easiest way to do this, and the way that most GIS software deal with it, is we actually only care about the corners. And in reality, we only really need 2 corners, but you can store all 4. Right? And so we have, for example, right, if this is our grid cell, if this is our raster data, right? So just to sort of clarify, right, how do we know the location of raster data? That's the question we're trying to answer. What we do is we apply coordinates on the 4 corners. So here, 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 and here, right? So this is going to be an X and a Y. This is going to be an X and a Y, an X and a Y, and an X and a Y, right? So rather than knowing the coordinates of anything inside of the raster, all we keep track of are the locations of the four corners. And then if we need to get down into the raster, we can use trigonometry and algebra to narrow it down. We're not going to go into that now, but just in terms of how rasters store their location, they only keep track of the four corners. So hopefully that makes sense. The last piece that I want to talk about is the trade-off between spatial resolution, cell value, and data volume. And so if we have, I'm going to grab our example from before here. I'm going to grab this example here and bring it down so we can talk about it again. Right, okay, so when we talked about cell value, right, we said that a value for a given cell represented the entire area under that particular grid cell, right? And we said that spatial resolution was the length of one side of the grid cell. So if we have a spatial resolution this big, right? Let's focus in on one grid cell. Right, we're saying that the cell value here, which we'll call X, right, represents this entire area. Now imagine that we generated a new raster, right, with a spatial resolution half the size, right, half the size. So if we did that, right, I'll go over here, right, this is our original grid cell. If we break it into something half the size, right, so each one of these is half the length of one side as the original, right? Now we've broken it into 4 pixels, each with different pixel values, right? Each with different pixel values representing the area of this smaller pixel. Let that sink in for just a second. As we decrease the spatial resolution, right, as we shorten the length of one side of the pixel, the pixel value or the cell value represents smaller and smaller areas, right? And so if we think about that in the context of, say, precipitation, right, as we shrink the size of the area that we're looking at, the pixel value or the cell value starts to become more stable, for lack of a better word, right? You start to begin to feel more confident that your pixel actually represents, that the pixel value actually represents the area underneath it, right? That in a larger scenario, right, what if there was an area that had a flood and an area that had no rain in the same pixel, right? That could happen. What would the cell value be? Well, it would be half, right? Because you have an area of flooding and an area of no rain. The pixel value in theory would be half. So you're averaging out across that entire pixel. So as we decrease the spatial resolution, right, we, in theory, approach a more accurate cell value. Let me specify that, right? As we decrease the spatial resolution, our cell values more accurately represent the area underneath them. Right. To summarize what this diagram is trying to explain, as we decrease the spatial resolution, the cell value begins to more accurately represent the area underneath it. Okay? So the question then becomes, well, why not just make the cells as small as possible every time, all the time? And there's a trade-off, right? As we decrease the cell size, or spatial resolution, right, we increase the number of cells needed to cover the same area. Right? And if we go back up here for a second, you can see this, right, visually, right? These two cells right here are the original spatial resolution. When we decreased the spatial resolution, right, we made 4 smaller cells that took up the same area. So it took 4 cells in this higher spatial resolution, right? We decreased the length of one side. We now have 4 cells for every 1 cell. So to cover this same area, we would need 4 times the number of cells. Okay, why does that matter? Well, when we're dealing with computers, right, each cell value takes up space on a hard drive. It's what we call memory, right? So as we increase the number of cells, we increase the data volume, right? We increase the amount of space on a computer needed to hold it and the amount of time it takes to deal with it. So we increase, right, this increases data volume. I'm going to underline this in red, right? Because this is a key limitation, especially when you're looking at large areas, right? Imagine, for example, we were trying to measure the elevation for the entire United States of America, the continental 48 states. Just keep it simple, right? In a perfect world, you could easily measure elevation every meter, right? So have a cell size of 1 meter. And that would not be outrageous in terms of, elevation changes every meter. That's not unreasonable. But just think for a second how many grid cells it would take to cover the entire United States if each grid cell was only 1 meter square. It would be astronomical, right? Your computer would not be able to handle it. You would have to start getting into supercomputers, and it would become very expensive and time consuming to process. So there's a trade-off between how small do we go, right? How accurate do we try to get in terms of getting these cell values to match the underlying reality versus how much data can we actually hold in terms of the volume of data that goes on the hard drive. I hope that made sense. And as always, if you have any questions, please reach out. Thank you.